Hello everyone. So welcome to this session, and in this session we'll be discussing about the three-dimensional viewing. So in the previous session we had discussed about viewing, and even we have discussed about the clipping of a point, a line and a polygon with respect to all those things whatever we have discussed. Either in the clipping or the viewing, it was with respect to two-dimensional. Fine. So now in this session we will discuss how we are going to make use of the knowledge or the information what we have gained from two-dimensional viewing into three-dimensional viewing. Fine. So as I have told, the OpenGL program is mainly focuses on 3D. Hence the 2D is a special case of a 3D. So where we just ignore the Z-axis. But when we bring in the Z-axis into the picture, that is where we talk about a three-dimension and a three-dimensional viewing. So hence in this session, with the understanding of a two-dimensional viewing and the two-dimensional viewing pipeline, we'll discuss and we will enhance it to a three-dimensional viewing. And so again I'm saying, so if you have understood a two-dimensional viewing, then this three-dimensional viewing session and this concept should be an easy concept for you to understand. Hence, so we'll just see. So as I mentioned, it is similar to 2D viewing. The only thing is I should somehow think how exactly I'm going to bring in the Z-axis into the picture. Fine. So now in this case, now just look at this. Whatever the clipping routines we have discussed until now with respect to 2D viewing or 2D clipping window, all those will stand as it is. Hence, so we have already know what are the clipping routines of 2D viewing along with the viewport, along with the viewing window, clipping window or any of those concepts. Fine. So now with this, as I told you, I need to add up few more concepts. So I just told easy it has a Z-axis. It is not so easy to just add a Z-axis and make a 2D viewing to appear like a 3D viewing. It's not so easy. So there are few conceptual things which we need to bring into account, and we need to see how exactly we are going to handle all those scenarios. Fine. Hence along with whatever we have came across with the 2D viewing, so we need to add up something on this, and these are the things which we need to focus upon when we talk about a 3D viewing. Fine. Hence, so now when we talk about 2D viewing, so never we concentrate upon a projection. Never we talked about a projection. Our main motto was here how we are going to define or how we are going to make use of a clipping window, so that we are going to have an object which can be visible and which should be eliminated. And so, but we never thought about a projection routines. But now it's the time when I bring in the Z-axis into account. Now this is the time where we need to think about the projection and the projection routines. Now this is where we talk about projection routines, because now just think, though we talk about 3D and though we talk about 2D, we all know the fact that whatever the display screen what we right now see, or tomorrow what we execute, and later on whatever we see on the display device, all those is a 2D plane. On a 2D plane, I use some concepts, I use some trick, I use some technique. So where I am going to transfer a 3D object on a 2D display screen, and it appears to be 3D. It is going to appear to be 3D. That is where we talk about the concepts, we talk about the techniques, the tricks, whatever you going to call this. But ultimately, this 3D should be projected on a 2D screen. Clear? And this is where we talk about a projection routines. Either we talk about a different type of projections or the techniques what we use, where we project a 3D object on a 2D plane. That is where we talk about a routines or the methods or a functions, and all this is required so that we can transfer a scene specifically right now, which is going to be a 3D scene, to a view on a planar surface. Why I'm calling this as a planar surface? Because the screen is a 2D. It's a plane. It's not a volume. It's a plane. Hence, we need to transfer a scene to a view on a planar surface. Hence, I need to talk about all these things. The projection routines, the projection methods, and so on. And apart from this, so now I'm going to have a cube, a 3D object. I am projecting it to on a 2D plane. So now just visualize, just imagine, when I say a cube, it has a front face, which you are seeing. It has a back face, which is hiding, which you are not able to see. And this, we call this as the invisible part, what you are not able to see right now. And whatever the face you are seeing right now of a 3D object or a cube, we call this as a visible part. And so now, what do I do with this invisible part? Should I display? Should I handle this? Should I eliminate? Should I clip out? Because anyhow at this point of time it is not visible. So I can do anything of my choice what I want to do with this. But which is the best one? Should I display and should I use it for later processing, which is going to cost for the efficiency and the time? If I'm going to eliminate this, surely I'm going to have good efficiency, but I'm going to lose the information. I'm going to lose the content of my scene. I'm going to lose the content of my object. So now what should I do at this point? That is where we talk about the visible part and what do you do with the invisible part of a scene. Clear? And whenever we talk about a 3D scene, if I just have a 3D object, it's not sufficient. And even if we are going to have a group of objects, even it's not sufficient. We need to bring in this to a real world environment. So where it looks similar to a real world entity, a real world scene. That is where we talk about the lighting effect. And when I'm going to have a lighting effect, each object can be defined with its own properties, own characteristics to be an object. Some object can be completely reflective, some object can be transparent, and some object can be rigid. These are the few properties which I can bring, and all these concepts will come into point only when you talk about some light effect in your scene. And again, this will be part of your 3D viewing. So right now in my discussion at this session or the coming session, I'll be focusing upon the projection routines. Later on, though I talk some part about visible parts, but later on in the later sessions, we'll discuss more about the visible part and the invisible part and how do we handle this. And even later we'll talk about the lighting effect, the light effect, and how we are going to give the surface characteristics or the object properties. Fine. So these are the few concepts which you need to understand and which you need to bring into the discussion when I talk about a 3D viewing. Fine. So now just focus upon projection routines, and these two just to understand, these are essential, which we'll discuss later. Fine. So now when I talk about a projection routines, so this is where we talk about a viewing. And so whenever we are going to have a viewing, there are different kinds of projections. I will come to that point later, but at this point, just look at this. What exactly you are seeing right now? An object which is going to be in its own coordinate system, and if you observe, I am not using only two axes. This is y-axis, x-axis, and if you observe, I have got one more axis also, that is the z-axis, which makes my object to appear to be 3D right now. And I am going to have a camera now. Fine. So until now, when I'm talking about a 2-dimension and its viewing, we never talked about, or we are never brought into camera into action. But without a camera in the action, without you discussing about a camera and its point and its position and the way it has been oriented, way it has been rotated, without considering all these properties of a camera, you cannot have a 3D viewing. You cannot have a 3D viewing properties. Hence the camera is going to play a major role. Hence, the camera is going to have its own coordinate system called as a reference coordinate system, and object will be having its own coordinate system. And both coordinates can be similar, can be same, which is by default, but we need to understand how exactly we are going to manipulate or play with this two coordinate system. Fine. Hence, we are going to have a view plane. Hence, a rectangular box, whatever we discussed in 2 dimension, that is whatever appears in this rectangular box should be displayed, and whatever is going to be out of this rectangular box should be clipped off. Fine. And that is where we talk about a view plane. Hence, if we talk about a camera, if you imagine how a pinhole camera is going to work, a pinhole camera is going to have a film at the back end, and whatever it is going to project will be imprinted on this film. It is similar to that. I am just saying about a real world camera, but synthetically if you try to map with a computer graphic camera, so this film, we can equate this with the view plane. Whatever is on the film, you get a photo of this. Whatever is on the view plane, you get an image of this on the display device. That is how we are going to relate a synthetic camera with the real world camera with the analogy. Clear? Hence, so now just understand with this, we need to discuss about the camera, how we are going to make use of the camera in our discussion. And that is what, when you talk about a 3-dimensional scene, it is not just adding a z-axis along with bringing in the z-axis into be alive. We need to set up a 3D coordinate reference. That is what a reference coordinate system is. And whatever the camera coordinate you declare, define and exhibit, that we call this as 3D coordinate reference. And we need to set up this first. If without setting this, you would be meaningless to call a viewing as a 3-dimensional viewing. Hence, we do this using the camera parameters. So we'll see what exactly parameters of camera is going to be later on. Fine. And by doing this, by handling the camera parameters, so which is going to define me what is the position of the camera, where do I place the camera so that I can visualize the scene or the part of the scene what I want to visualize, and how do I exactly orient the camera so that I can visualize my object in a particular angle, and we are going to put it on the view plane. Fine. And so now the position of the camera, the orientation of the camera will decide now what part of the scene should be on the view plane, and this view plane is also called as projection plane, and analogically, or if you relate this, we can call this as camera film plane. Clear? Hence, you need to understand what is projection plane and the view plane. Whatever the clipping window, the clipping area we talked about earlier in the 2D viewing, I can relate that similar to as projection plane in 3D viewing. And so with this, now just observe here. So as I told you, when I talk about projection in 3D, we can talk about different types of projection. So this leverage was not in a 2D viewing, because in 2D viewing you never think about all these projections, because 2D is not a real world object. Though a 2D screen exists, but other than this, no 2D exists in the real world. Everything is a 3D object. And how exactly our human eye is going to preserve, or how is going to have its perspective of viewing the objects, it depends upon different types of projections. Hence, the parallel projection is not a real world projection, whereas the converging line projection is a real world projection. I'll just show you an example what exactly this two is going to be. Look at this two diagram. I hope this should give you enough clear information what I'm talking about a parallel line and what I'm going to talking about a converging lines. Look at this two. Look at these two diagrams. Fine. So now in this diagram, you can just see I'm going to have the parallel lines. The camera is somewhere here, I don't know exactly where the camera is, but the camera should have a position. Hence right now I don't know where the camera point is. Hence we say the camera is going to be at a distant distance. Fine, I don't know where it is. It's an infinite distant. But camera exists. Camera somewhere exists. So now hence I don't know where is the position of the camera, but I know what is the direction of the camera. Hence in parallel lines we will only know what is the direction of the camera, but you will never know where the camera is or what point the camera is starting to emerge lines of projection. Hence for that reason all the lines will appear to be parallel. So I am going to have projection line, projection line, projection line, projection line. Every line now, if you just look, every line is going to be parallel now. Hence that is where we call it as parallel lines. Now whatever the object is going to be in the scene will be put onto this clipping area or the view plane. You can see now this object is not inside this cube or inside this area. Hence this is clipped off. That is what we say clipping out. Hence if you observe the object size at this point and here, it's going to be almost similar. It's going to be almost similar. The object, so now this is farther than this object and this is near to the view plane, but the size is still same. The size doesn't matter because of parallel projections. At the same time, just compare this over here. Now I know where the camera is and even I know what is the direction of the camera. Hence when I know where the camera is, that is the point where the projection lines will emit. Hence we say all these lines is going to converge at the camera point. Hence we call this as converging lines. And if you observe, so this back clip area or the back view plane is larger than the front one because of the converging lines. Hence now whatever you're going to see on this plane is going to appear, the object appears smaller as it is going to be closer to the camera point, and as it moves away from, is I'm wrong? Yes, I'm wrong. So the object is going to appear larger as it is going to move towards or as it is positioned nearer to the camera, and the object is going to look smaller as it moves away from the camera. And once the object will go out of this particular view area, that is where we are going to clip it out. And that is where we talk about the parallel lines. The projection lines are parallel in this case because I don't know where the camera has been positioned. But in this case, I know where the camera is, and that is the point where the projection line starts emitting. Hence, this is where we talk about parallel and converging lines. So keeping this concept into mind, so now I can introduce you two types of projection. So please remember this two type of projection, which we can make use of this for the further discussion. Hence, so we are going to have a parallel projection and we are going to have perspective projection. Hence the parallel lines, we call this as parallel projection, and this is a perspective projection. Clear? I hope it's clear for you with respect to projections. So now with this projections, so now we'll just talk about the object once it is projected using either a parallel or a perspective, irrespective of that. An object, a 3D object has been projected. Just look at these three diagrams what I have been put over here. I'm just going to have a pyramid. So where we are going to have a set of 4 triangles as the 4 faces, and the base is going to be a square. Just look at this 3D object. And right now if you just visualize this, how exactly you're going to perceive this now? How exactly you're going to perceive this? So whether this tip is far and the base is nearer. At some point you visualize something like the tip is far and the base is nearer. But if you carefully observe in some other angle, you'll perceive even that the base is farther and the tip is nearer. So there's no clear distinction between this. And hence this is going to be a parallel projection. and even if it is a perspective projection, it is going to be hard for me to exactly tell which is the front point, which is the back point, which should be the visible, which should be invisible. And now, but if I try with this, I'm just going to get, so now in this case also I'm not able to clearly tell, but what about this invisible line? Should I eliminate this or should I display this? And right now, if you just visualize this object, now this is going to clearly tell the base is below, the tip is above. And so by this we can say the base point, the center of the base point and the tip of this tetrahedron or the pyramid is going to be exactly in line intact. And this face is, this point is nearer and this point is far comparatively to this point. And so now when you have such cases, so all these three are the same diagram. So no orientation has been changed, no angle has been changed, no point has been changed. But what has made us to visualize these three types of object which is similar type, but it has been clearly distinguished. How it has been distinguished? Because in this case you are not displayed the invisible line of an edge. In this case you have made all the edges to be visible, and in this case you have removed the baselines. So just how we are going to handle with this. Now this is what we call this as depth queuing. Fine. So now just a small and technique answer for this is how do we install the depth queuing is that just observe here. Fine. So now I'm just going to have set of lines which is nearer and one which is farther. The line which is nearer has got highest intensity, and as the edge moves farther we're going to have lower intensity. Hence this is the one technique where we are going to use to solve the problem of depth queuing. Fine. So that is to understand which is point is nearer, which is point is farther. We use the one technique where we are going to have high intensity for the point or the line or any object which is nearer, and low intensity which is going to be farther. And that is where we are going to have maximum and minimum intensity value of an object. And along with this technique, I can use different types of techniques. I can highlight the visible lines in different color and the invisible lines in different color, so that I can perceive which line is front face and which is in the back face. And even the other techniques are non-visible lines can be displayed as in dashed lines, and somehow we can remove the non-visible lines. I can use any of these different approaches so that we can going to handle the depth queuing. Fine. Now this is where a short form how we are going to handle invisible faces or invisible part of the objects, but we'll discuss more about this in the coming sessions. But right now this is what you need to understand at the abstract. So now, as I told you, whenever going to talk about a 3D viewing and its pipeline, camera plays a major role. So where the camera is, first you need to set up the position, you need to orient the camera, that is where it decides what is the reference coordinate system is. Hence I am going to have a camera. Now this camera should be positioned and this camera should be oriented. That is, I can move the camera wherever I want in the scene. I can orient the camera in whatever the angle I want in the scene, so that I can see part of the scene which I am interested right now to visualize. And here I can position wherever I want in the coordinate system. I can orient the way I want the camera. That is where your first job is. You need to position and you need to orient. Something like I have positioned the camera something like this, and I oriented the camera in such a way that it should visualize this entire house or part of this house. And if I just tilt the camera, if I move the position of the camera, you may not see this house in your display window. That is how the camera is going to play a major role. Hence, so now when I use the camera, up direction is going to be an important one. You need to clearly tell what is the up direction. How do you? So usually you don't reverse the camera. So if you talk about real world thing, so usually in the case you don't reverse the camera. If you reverse the camera, the entire image will also be flipped off. So usually we don't reverse the camera. Hence, first point is keep the camera intact and tell me what is the up direction of the camera. Fine. So later on you talk about position, orientation, so on. But first decide what the up direction is going to be. Based upon that, your scene should be designed. Based upon that, your scene should be visualized. And so now, when you are going to have a camera, I hope you know what is shutter of a camera. So whenever I want to take an image, the shutter will be opened, the light will enter into the camera, the image is captured, immediately the shutter closes. This is what we call the shutter of a camera, pressing the shutter button of a camera. Hence, this is what the shutter does. I've just given animation to show you what is a shutter. It's opening the camera and closing the camera. When it opens, light enters, image is formed. When it closes, nothing enters, no image is formed. Hence, so whenever a shutter has been activated or whenever the shutter is opened, we are going to take an image, and whatever the image we are going to take, it is going to crop from the scene and will be placed on the clipping window. For example, if this is the entire scene is not captured. I am not capturing the table, I am not capturing the background, anything. I am just capturing what I want to capture in this frame. Remaining all the objects in the room, in the scene, will be eliminated. That is what now we can view this as a clipping window and what exactly we are going to crop into. Clear? And so just clearly understand how the camera is going to work with your actual computer graphics object in 3D viewing. So now when you talk about actual camera, so the actual camera, now we are moving towards synthetic camera, and if I just compare, so when I say synthetic camera, it's an artificial camera, and what we discuss it as a concept or a component in computer graphics. We are bringing the actual camera into my digital world, and now in digital world it just becomes a synthetic camera and an artificial camera. And so now if it's actual camera and if I compare with the synthetic camera, being a computer program and the graphics programmer, it's my camera now. Hence it's our camera now, more rather. So hence we have more flexibility and more option for generating views of a scene with computer graphics program than we do with a real camera. So now if I'm going to have a real camera, you have only limited options, limited flexibility to play with this. But you have a lot of options to play with if you're talking about a synthetic camera with respect to computer graphics program. And what are those? I'll just list a few. The first thing, we can play with projection, parallel projection or perspective projection. We can make a choice out of this. If it is an actual camera, if it's a physical camera, every time it's going to be a every time it's going to be a perspective projection. There is nothing called as parallel projection in your actual physical camera. But if it is a synthetic camera, with respect to computer programming, now you can choose a parallel projection or you can choose a perspective projection. This is the one flexibility what we can have. Other is, so selectively we can eliminate the part of a scene. So if you're using an actual camera, so you cannot selectively eliminate. Whatever you focus and whatever the object will be in the scene, all those will be part of the scene. I'm going to focus at 10 objects right now, and out of those 10 objects, if I want to remove an object from the scene, it's not possible. But if it is a computer graphics program and a synthetic camera, I can use the technique and I can remove an object, keeping all the 9 objects intact by just removing one object. Fine. And move projection plane away from the camera. So now the lens and the display is fixed here. You cannot move this out of camera. But now I can place a projection plane with the camera position or move away wherever I want. I can put this projection plane in front, or I can make this projection plane to be at the back of the camera wherever I want. Hence, I can move the projection plane away from the camera or into the camera or wherever I want. Fine. So now once we are going to have this, we can, as I told you, the projection plane can move anywhere. Even I can get the picture of the object in back of synthetic camera. A few of the flexibility what we can bring in if you're talking about a synthetic camera with respect to computer graphics program. Fine. So now with this camera properties, now we'll discuss about 3D viewing pipeline, and it's similar to 2D viewing pipeline. If you remember the 2D viewing pipeline, so we are just going to have modeling coordinate system. From modeling coordinate we're going to have word coordinate system. From the word coordinate we are going to have the projection coordinate, the view coordinate, and so on. It is similar to this again. It's similar to this. We are going to have modeling coordinates. From the modeling coordinates we are going to have modeling transformation, which will give me word coordinates. So this word coordinate will be transferred into viewing, hence we call this as viewing transformations. Hence we are going to have a viewing coordinate system now, and from viewing coordinate system we are going to have the projection transformation, that is either parallel or perspective or whatever you call. Hence we are going to have the projection coordinates after this block. And with this we are going to have normalized transformation and clipping, where the exact clipping operation will be performed. So the part of the object should be visible and part should be eliminated. And once this is done, we are going to have normalized coordinates, and this normalized coordinate is going to be the viewport transformation. And finally, once we are going to have a viewport transformation, we have device coordinates, which we are going to map this on the device and display the part of the scene or the entire scene, whatever you have been chosen. So this is again similar to 2D viewing pipeline, and this is the 3D viewing pipeline for you. So now with this, when we talk about 2D viewing pipeline, we talked about clipping area, or we call this as clipping rectangle. Fine. So you hope you remember this clipping rectangle. So now when I talk about a 3D viewing, it is no more just a rectangle. It's going to be area. It's going to be volume. That is what I told you when I showed you the picture examples for parallel projection and perspective projection. The objects, if it's within the area, will be visualized. If not, will be clipped off. That is where we talk about area. Now we are going to have 4 faces side by side, bottom and the top, and this we call this X minimum face, X max face, Y minimum face, and Y maximum face. Fine. Along with this, we need to bring in the Z axis, hence we are going to have 2 more faces, the near face and the back face. So back face is Z minimum, near face is Z maximum. So now, until now we were calling this as clipping rectangle. Hereafter we are going to call this as clipping volume. Fine. And if it is a parallel projection, the front face and the back face is of the same size. If it's perspective, so now this face is going to be smaller. The face which is near to the camera appears to be smaller, and the face which is going to be away from the camera will appear larger. Fine. So this is where we are going to have the viewing volume or the clipping volume when you're talking about a 3D viewing and its pipeline. Fine. So now with this, we are going to talk about the references of a point or an object where we define. Along with this, as I told you at the very first minutes of this session, I told you we need to discuss about the camera and its reference coordinate system. Hence right now whatever you are seeing, you are going to see 2 coordinate system. One is the object coordinate, and we are going to have the reference coordinate, and we call this as viewing coordinate. And the viewing coordinate has got set of parameters. So if I play with these parameters, if I'm able to manage these parameters, we are be able to position the camera wherever we want, and we can visualize whatever the part of the scene we need to have. That is where we are going to have P0, the point, reference point where the viewing starts, and a point which should be visualized or not, depends upon this orientation. Hence we call this as viewpoint, or we call this as viewing position. And this is going to be again in 3 dimension, the Z view, X view, and Y view, whereas this is the window coordinate. XW, YW and ZW. This is where you define the object and this is where you perceive the object. Fine. So now this viewpoint is also called as eye point. That is the view from where we start, the point where we start viewing the object. Hence this can also be called as eye point, or even this can also be called as camera point, because the camera is the one which is going to view, the camera is the one we need to position, orient and so on. Hence we can even call this as camera point. And whenever we are going to have the camera point, I told you need to with positioning and orientation of the camera, you should decide what is the up direction of the camera is going to be, and that is what we are going to have view up. Fine. So we need to say what is the up direction. Usually we pick the y-axis as a view direction. Wherever the y-axis will stay, that is going to be the view up direction for me, and this is what you need to have the view up. Along with this, you need to have the view direction. As I told you in parallel projection, I don't know where the camera is, but I know what is the direction of the projection, direction of the view. Hence I need to have what is the view direction. It can be true either in parallel or in the projection. Clear? Sorry, parallel or the perspective. Hence even I should know what is the view direction. Hence there is a few properties which we are going to have. We are going to have viewing position, which can be called by any of this name, and we are going to set up what is the view up or the up direction of a camera is going to be, and what is the view direction of the camera is going to be. So now with this, so now if I am going to have this properties, so usually we are going to have view plane, that is the projection plane which we discuss or which we try to project upon. So now whatever the projection plane we discuss, the view plane discussed, so this should be parallel. This should be parallel with whatever the front face and the back face we are going to talk. And so every time by default, the view plane, the projection plane is going to be with the XY axis, hence we call this as XY plane, and the Z axis is going to be perpendicular with the view plane. By default, every time the Z axis is going to be in parallel or in perpendicular with the view plane. Hence just keep this one point, hence we call this as projection plane. And so now just look at this. The y-axis will be the up direction of the camera, and z-axis will be the direction of the camera, and where this view, z view, should be the perpendicular line for the xy plane, and from where the direction is going to come, in what direction we are going to view. So this parameter is going to decide for us. And so now whenever we are going to talk about projecting some object with respect to this reference coordinate system of a camera, if I want to put this on a display window or should be displayed on a view plane, that is where we are going to have normalization coordinate. Hence we are going to have normalized window. Hence the normalize is going to be again perpendicular with the projection plane. Every time it is going to be in perpendicular with the projection plane, the normal vector whatever we're going to choose, something like this. I'm going to have X, I'm going to have Y, I'm going to have X. If you just look this planes, this will be defined with the XY axis, and where it should be positioned, what is the direction will tell me what is going to be in the Z axis. Hence I can place it at the origin or the point of the camera where it is. So I can have the projection plane on the camera, or I can have the projection plane in front of the camera, or I can have the projection plane at the back of the camera. Now you can decide where the projection plane should be. Hence, so when I'm going to talk about a view plane and a normal vector, wherever the Z axis is going to be, the normal will always be intact in line with the Z axis. Hence, the Z axis will define what part of the object should be visualized onto the projection plane. Hence, this normal point, whenever the normal is going to point towards the reference point of the camera or the camera point or the viewpoint, this point we call this as lookout point. Remember this word, the point where the normalize will again point it, we call this as look at point. Now this is the point which will tell me what exactly I am looking at. Hence we are going to talk about this, and we are going to have UVN, viewing coordinate reference frame. Whenever we're going to talk about a reference coordinate, this is what we are going to call this as UVN. So this V vector V is going to be the y-axis, which is the up direction. Hence up vector will be as V, and the z is the normal vector usually will be intact with the z-axis. Hence we call the normal vector n intact with the z-axis, and the direction vector now will be with the x-axis. Hence these are three parameters of any 3D viewing what you're going to have. Hence we call this as UVN, viewing coordinate reference frame. U stands for direction, V is going to be the up vector, N is going to be the normal vector. Clear? And so now with this UVN, so now whenever we need to compute what is the normal is going to be, normal point is going to be, we are going to consider normal vector, and we are going to consider number of elements in normal vector and compute what is normal value. And the up vector, use the vector V and use the normal value, you are going to find U. And so once you know what is the normal value, once you know what is the up value, use this where we are going to find the V and where we are going to find the up vector. Using these two values, I can find what is the up vector. So this is how we are going to find what are the properties of UVN is going to be. And so now once you know how to control these values, by varying the viewing parameters, we can obtain different views of the object in a scene. So if you know what is direction vector, what is the up vector, what is the normal vector, by just modifying these values, we can have different types of views in the scene. That is how we are going to handle the normal, how we are going to handle the up vector, and so on. So for just an example, just look at this. I am going to have the camera is going to be at this position. Later on I will be moving the camera to this position, but if you observe, the normal is constant. It is going to be constant with the x-axis, sorry, with the z-axis or any axis what I am going to consider. The normal will be intact with any one of the axes. By default it is going to be z-axis, and even if I am going to move the camera at any direction, so the view will not change, but only the object in the view and the scene will change. And this is where if I keep the normal constant and if I change the position of the camera, we are going to have a pan effect where we can have part of the scene can be moved or visualized in sequence. Fine. And now if I don't keep the normal vector constant, if I change normal vector with respect to axis, right now it's in z-axis, later I'll move on to the y-axis, and later I'll move on to the x-axis. If I keep on varying this, then I am going to view the object from the front face, view the object from the side face, the same object from the other side. Hence, so by not keeping n constant and varying the n vector, I can view the object in different directions. So this is how we are going to have different view of the scene in your computer graphics. And so now whenever we talk about 3D viewing, so these parameters are essential. How do you handle a camera? What are the different types of projection? And how exactly you are going to make use of these parameters. The U parameter as a vector, V parameter again as a vector, and the N parameter again as a vector. And how do you vary this? Now this is what you need to understand, the basic of a 3D viewing. So in next session, we'll focus upon more concepts about 3D viewing. Thank you.